Um, Welcome to our live solve.
Yeah,
Good
hi
to
everyone.
it's good to well not see you guys, but it's good to be able to like meet with everybody.
Yeah, for sure.
And our icebreaker today is about the daylight savings that just started last week, I think. So, what do you guys think about daylight savings?
Yeah, Erica, do you have any thoughts on this one?
Um, I think I don't know. It's like on the bright side, when I wake up, now it's like it doesn't have to be pitch black. But on the other side, it'll be like 4 p.m. and the sun is setting, and I'll be like, okay, so do we really need to do this?
Yeah, that's true. I feel like this switch I prefer because I get a little bit more sleep in the mornings. When it switches back, that's like terrible for me. I hate the losing 1 hour of sleep.
Maybe it should just be the same across the
Yeah.
entire year.
I see I see a lot of mixed opinions. Seems like
Mm-hmm.
people are saying it sucks, they love it, neutral,
Usual.
interesting. Yeah, it's true that I do enjoy that it's like bright in the mornings now, because like last month it would be kind of still a little bit gloomy in the mornings, and then
Right.
I wouldn't feel like energized to start my day. So
Yeah, sure.
there are some
Wait,
perks to it.
yeah, I hate it when I'm in school and I look out the window and it's like pitch black. Like, do I need to be in school right now? Like, can I
Yeah, I
leave?
know. Oh my goodness. Especially if you do stuff like after school and it's already really dark out, like sports and stuff.
Oh, wait, Kira said something interesting about how like it looks like car crashes and stuff go up during daylight savings, which is well, I've never actually heard of that. That's very interesting.
Yeah, that's actually such an interesting point. I hate, do you have your driver's license, Erica? I
No, wait,
recently
I have my permit, but I haven't been able to get around to getting my lessons yet because I'm like,
mm,
okay, I don't want to spend money. But
yeah, that's real. I just recently got mine. Well, I guess it's not that recent anymore, but like a few months ago, like 6 months ago. But I haven't gotten that much time to practice driving around. But yeah, I
mm,
hate driving in the dark. I can't see the
oh
lines on the
yeah.
road, so it
Uh-huh.
makes it really difficult to like stay in my lane.
Yeah, for sure. And like I feel like these days, like people's headlights are so bright, especially at night. It's like I'll see a car coming at me and it's like literally I can't see anything else on the road. Like these headlights are way too bright.
Hmm. All
And
right. I guess we
what
can
else?
transition into just like introductions. So right next to me is Erica. She is heavily involved in a lot of math and computer science clubs at her school. She also did BU Rise last summer, which is like a really cool summer camp. She's very interested in the intersection of numbers and technology and how they interact with the world around us. She's qualified 3 times for Amy. She earned a perfect score on the Rose Holman math competition. She's the top scoring female in her AMC region. She loves reading and is an inline skater. Whoa, that's really cool. And she won the F16 to 17 age division in North America's largest inline half marathon, North Shore. Oh my gosh, maybe you can tell us more about that.
Oh, it was kind of I made it sound more impressive than it was. There was like maybe like 10 people total in that age group. So like wait. Um anyways, hi guys, this is Cynthia, and she is also a senior, I believe, in high school, and she lives in Massachusetts. She has been involved in competition math since middle school and is a two-time Amy qualifier, which is super cool. And she loves number theory and attended Promise over her sophomore junior year summer, which is also a really fun summer math camp. So that's super awesome as well. And it says here that she was also a MIT Prime Circle Scholar in 2023, which I don't know too much about, but that sounds super impressive. So super good for you, Cynthia. And maybe you could tell us more about that too. And outside of math, it says that Cynthia enjoys playing the violin and swimming for her school, and she currently plays in the Boston Philharmonic Youth Orchestra and has played in the Massachusetts All-State Orchestra three times, which is super awesome because I've heard that like a lot of all-state orchestras are really hard to get into, and especially Massachusetts, which is like super competitive. So that's super awesome. And
Thank
she
you.
also enjoys reading, biking, and playing tennis in her free time. So
Ooh, I see a lot of people also play violin, which is fun. Yeah, I love the violin. I feel like music is a good way to unwind and, get in a good headspace. All right, Erica, do you want to get us started with the problem solving?
yes,
Since
sure,
that's what this
okay.
live solve is all about.
Yes. Okay. So we are going to be going over the Math League 2025 Math League problems. And so, just so you guys know, we have not solved these problems before. We are going into this completely like we are starting from a baseline as well. Like we don't know the answers to these. So we are solving them with you, and that is the goal here. So our first question, we're going to start off from the beginning. We're only going to be solving the even problems today, by the way. And our first question is number 2. So Silas scores 97, 94, 96, and 99 points on his first 4 math quizzes. However, he gets sick right before his 5th quiz, so he only scores 23 points. At least how many points must Silas score on his 6th quiz for his average number of points earned on all 6 quizzes to be at least 80? Okay, so, tough question. Does anybody have any thoughts on how to start this problem? I'd like to hear from all of you guys. The first hand I saw was okay, and I super apologize if I say your name wrong, but Smriti, would you like to unmute and tell us like how to do this problem? Okay, and I'm seeing a lot of answers in chat too, so that's super awesome. Um,
I think it seems like they can't unmute, so maybe we should just run through the solutions.
yeah, okay, sure.
Especially just like in the interest of time too.
Oh, okay, it looks okay. Yeah, it looks like they can mute. So I'm seeing a lot of stuff in chat about how we want to add up all of these numbers. And so shout out to all of you guys because that definitely sounds like a very good starting point. So from here, I don't know, I would want to work backwards. So we know that the question is asking us how many points must Silas score on a 6 quiz for his average number of points, well, like to be at least 80. And so now I want to know, so what does this, if it's what his average number of points needs to be, then like how much does that like how much does that equal to? How many points does he have to score across all 6 of his quizzes to be at least 80? And because of how averages work, we know that if his average points number of points is 80, then his total number of points must be 80 times the number of quizzes, 6. His total number of points must be at least 480. And we see here we know 5 of his quiz scores. So now we just need to find out what does the sixth have to be for our final sum to be at least 480. So for example, okay, so we have 97 plus 94 plus 96 plus 99 plus our fifth score 23, and then and that entire sum. Does anybody have that sum for me? Okay, 409. Thank you to like everybody in chat who answered that. 409. Okay. I'm gonna trust you guys on this one for 409. This is if our sum for all 5 of these scores is 409 and we need to get up to 480, then the score that Silas has to score on the 6th quiz has to be at least 480 minus 409, which gets us to 71, right? And shout out to Shu and Cece who both got that in chat that I can see right now. Oh, and a ton of other people who also got it. Shout out to you guys too. And Caleb, to answer your questions, yes, you can get 2 stars. Well, on one chat message, no, but you can get a bunch of stars across the entire class. So just to check, is 71 our actual answer? Okay, it looks like it is. I have to zoom in on this, but it looks like 71 is our answer. So awesome. Okay, Cynthia, do you want to go over the next one?
Yeah, of course. Okay, so our next problem is the number 192 has n positive divisors. Let m be the greatest common divisor of n and 343. What is the units digit of m to the nth power? Okay, let's start off by just finding what n is, which is how many positive divisors does 192 have? And we can do that by trying to prime factorize this first. So I noticed that this is even, first of all. So I can factor out a 2, and I'm left with 96. And 96 also has a bunch of 2's in it. It's also a multiple of 3. So once we do all of this, we should find that 192 equals 2 to the 6th power times 3. And you guys can try and verify that on your own. But then once we have this prime factorization, in order to find the number of positive divisors of our number right here, we can just add 1 to both of the exponents and multiply those together. So 6 plus 1, and then we have this imaginary 1, right? Because 3 to the first power is just 3. So times 1 plus 1, that gives us 7 times 2. So 192 has 14 positive divisors, so 14 is n. And then m is equal to the GCD, or the greatest common divisor, of 14 and 343. Now, you might recognize 343 as 7 to the third power. It's good to have a bunch of the powers of primes kind of memorized so that you can recognize them. And I also see that 14 is 2 times 7 from what we have right here. And that means that the GCD should be equal to 7. So m to the nth power is 7 to the 14th power. Now, this is a really big number, so instead of trying to multiply this all out and then finding what the units digit is, let's just focus on the units digit patterns of powers of 7. So if we look at 7 to the first power, we get 7. 7 to the second power is 49, which has a units digit of 9. 7 to the third power has a units digit of 3. 7 to the fourth digit has a units digit of 1. And then we notice that since it's 1, it's just going to repeat and loop back every 4, right? So we look at 14. 14 was, it's 2 more than a multiple of 4, which means we're just going to go through this 3 times, and then we're going to end up in the second one here. So this is going to have a units digit of 9. Hopefully that makes sense. And let's just check to make sure that we got the right answer. And yeah, it looks like it's 9. So I'll toss it back over to Erica for our next problem.
Okay, awesome. Sorry, Taratula ate my mic for a second. I had to get that back on track. Okay, so our next problem, number 6. So we have a bowl of grapes. This bowl contains 5 red grapes, 4 green grapes, and 3 black grapes. Gary randomly chooses 3 grapes from the bowl without replacement. What is the probability that he chooses 1 grape of each color? Express your answer as a common fraction. Okay, so this is so I kind of also need to think about this. And if anybody has any ideas, feel free to like send them to chat relay. So so we have our bowl, we have our different colors, and he is choosing 3 grapes from the bowl without replacement. So right now, the only the only thing that I can think of is like casework, but maybe that's not the most efficient way to do this problem. So does anybody have any ideas for the method? Okay, so I'm okay. So maybe if we look at all of the different potential cases, okay, this is gonna be a lot of cases, but I'm gonna say, let's say our first case is that Gary first chooses a red grape, and then a green grape, and then a black grape. And then all of these different cases, we have six different cases, right? Because we have three types of grapes, and we have six ways to rearrange those three grapes, three colors, however we want. And so our other cases could be like red and then black and then green, or black and then red and then green, black and then green and then red. This I think definitely looks a little bit like inefficient, but I feel it in my heart that there's probably a pattern here. So and then okay, and then our last case is green. If we start with green, we have green and then black and then red, and then green and then red and then black. And so these are like all of the possible ways that Gary could be choosing grapes, and they're all different colors, right? And now I want to look at what is the probability that all of these cases are happening, that any of these cases are happening. Okay, so case one, our total number of grapes first is okay, and I think this is what you guys meant by add them all up, or at least this is how I would start. Our total number of grapes is 12, right? Because 5 plus 4 plus 3 is 12. So the chance that Gary first pulls a red grape is 5 over 12. Right? And I hope that red shows up on my screen. I think it does. Okay. And then he chooses a green grape, which would be, well, there's four green grapes, but since there's no replacement, the probability of him choosing a green grape is going to be 4 over 11 because there's only 11 grapes left. And then in a very similar like line of thinking, there's three black grapes. So, oh my god, okay, that blue does not show up well. Maybe this blue works better. Okay, I think it does. It looks a little turquoise though. But there's three black grapes and there's only 10 grapes left to choose from, right? So this is the chance that Gary will first choose a red grape, then a green grape, then a blue grape. And after this, I'm going to take a look at our second case, and then I'm going to talk about the pattern that I think I'm going to see here. So again, chances of picking a red is 5/12 times chances of picking a green, a blue, which is 3 out of 11. Oh, that is not blue. Is 3 out of 11. And then chances of picking a green is 4 out of 10. And we see here, okay, I'm starting to see these are going to be the same number, right? No matter, okay, these two, even in these different cases, in the end, because we are multiplying these three probabilities, these three fractions together, we are going to get the same fraction in the end. Because no matter what, in our numerator, we're going to have 5 times 4 times 3 in some order, and then we're going to have 12 times 11 times 10. Like in RGB, it goes 5 times 4 times 3. In RBG, it goes 5 times 3 times 4. In BRG, it's going to go like 3 times 5 times 4 or something. But no matter what happens, the chances of any one of these six cases happening is going to be, I'm going to go back to my normal green, is 5 times 4 times 3 times all over 12 times 11 times 10. And so this is the probability of, oh, wait, I shouldn't box that. This is the probability of one of these cases happening. And there are six total cases, and these all cases all have the same probability. So what we're going to do is we're going to multiply this chance of a single case happening, our 5 times 4 times 3 over 12 times 11 times 10. We're going to multiply this by 6. And I see there's a lot of things that we can cancel out here. So I'm going to take this 6 and I'm going to take the 6 and I'm going to cancel it out with a 12 to leave a 2, but then I'm going to cancel out the 4 with this 2 and this 10 over here to leave a 5. So now we have 5 times 3 over 11 times 5, and so we can cancel out this 5 again. So I get 3 out of 11. Oh, okay, this is not showing up very well. Okay, 3 out of 11. And okay, and we're going to see if this answer is correct. And okay, yay, it is. So I did see a few messages in chat about how we might be moving a little too fast. So I was wondering, is there anything that you would like us to recap from the first two problems? Just like very briefly? Okay, so if anybody does have any of those concerns, feel free to like send those in chat and we will address, and I'll try to like address them after the next problem. But Cynthia, do you want to handle the next problem for now? Oh, Cynthia, I think you're muted. I think Ratchet ate your mic
Oh
too.
yeah, I'm actually ate my mic. Yeah, of course. One thing I noticed that a lot of people put 1 out of 22 in the chat, and I think that might come from not multiplying by 6 for all the different cases that Erica just wrote on there. So if you multiply that by 6, then you should get 3 out of 11. And moving on, okay, we have a very long one now. Max the Magician has 5 not necessarily distinct positive integers a1, a2, a3, a4, and a5. And they have the following properties. A1 has a remainder of 1 when divided by 3. Oops, I'll just write this as 1 mod 3. A2 has a remainder of 0 when divided by 3. So 0 mod 3. A3 has a remainder of 2 when divided by 7. A4 has a remainder of 6 when divided by 7. And A5 has a remainder of 7 when divided by 9. And we're using just this information and the fact that an can't be a perfect square. And we're trying to find what n is. So we can just go through these different A1, A2, A3, A4, and A5 and see which one can't possibly be a perfect square. And I think the easiest way is just eliminating ones that we know can be perfect squares. So for example, our first one is 1 mod 3, which means it has a remainder of 1 when divided by 3. So an example of this would be 16, which is 4 squared, right? Because when you divide 16 by 3, we get a remainder of 1. So we know that it's not a1. And now looking at a2, which leaves a remainder of 0 when divided by 3. Well, 3 squared is 9, and 9 leaves a remainder of 0 when divided by 3. So it can't be a2. Moving on to a3, which leaves a remainder of 2 when divided by 7. Well, again, going back to 16, which is 4 squared, is 2 mod 7. So it can't be a3. A4 leaves a remainder of 6 when divided by 7. I can't find one that violates this one. So let's move on to 5, and if 5 doesn't work, then we can be pretty sure that 4 is the correct answer. But let's look at 5. A5 leaves a remainder of 7 when divided by 9. Um, well, 16, just like the other two, is 7 mod 9, and that's 4 squared. So 5 also doesn't work, which means an has to be a4, and that means that n is 4 for this problem. Hopefully that makes sense, and let's check. I see a lot of people putting n equals 4, so feel confident. Okay, cool. Nice job, everyone. And yeah, back to you, Erica, for the next one.
Okay, awesome. So this one was number 4. And okay, now we're on to number 10. Jack is painting a set of 15 identical cube-shaped blocks, and he needs to paint every face of each block. The blocks have edge lengths of 8 inches, and given that each bucket of paint covers 140 square inches of area, at least how many whole buckets of paint does Jack need to paint all of his blocks? Okay, so first I see, okay, so we have a ton of blocks, and we're looking at the surface area of these blocks because Jack's trying to paint all the way around these blocks, right? So first, okay, the first thing that I'm thinking of is I need to find the total surface area that he needs to paint. So the surface area of all 15 of these cubes added together. And then I would need to divide that by 140 because that's how much each bucket of paint covers. Yes? So we first start by finding out our total surface area. And for each individual cube shape, the surface area should be, okay, if we have a cube here, oh, this is a very, very bad cube, but, and our side length is 8, then our total surface area should be 8 times 8, okay, so 64. And then that is going to be the surface area of one face, right? And then we multiply that by the total number of faces, which is 6. So 64 times 6 would get our total surface area for one cube, which, okay, see, I could multiply this out, but since we're going to have to divide at the end, I might just leave this in like, as like a bunch of numbers. Okay, so 64 times 6. And I'm actually going to say, okay, so this is our surface area for one cube, and then for 15 cubes, our surface area should be that times 15, right? So that is going to be the total surface area that Jack is going to need to cover with paint. And then if each bucket of paint that he has covers 140 square inches of area, then Jack will need this giant number divided bad line, divided by 140 buckets of paint to paint all of his blocks. Like, is that checking out? So now that I have this expression for our total number of buckets of paint, now I need to actually do the math, which is going to be the hard part. Okay. So because I don't like dealing with big numbers, I'm going to break all of this into factors, okay? And 64 times 6. Okay, 64 is the easiest thing I can think of right now is 8 times 8. I could make this even smaller. I could make it into like an actual prime factorization. That would be like a bunch of 2's, but I'm going to leave it as 8 for now and we're going to see what happens. And then times 6 times, okay, 3 times 5. And then all of this over, okay, 14 times 10 looks like the easiest bit of like breakdown that I can see here. If we want to be super thorough, again, we can like break this down into prime factorizations, but I'm lazy, so I'm just gonna do whatever I can until I can see the factors that I can cancel out very easily. Like I can see that I need to cancel out this okay, different color. Okay, I need to cancel out this 5 with this 10, and that leaves us with a 2. And there's a bunch of 2's over here with the 8, and the 6. So I'm going to cancel this 2 out with the 6 and leave a 3. And there's one more 2 in the 14. So I'm going to take this. This is 4. And this leaves us with 7. So our final fraction is going to be something something 4 times 8 times 3 times 3 all over 7. And that should be, well, okay, I still have to do nasty math, but it's like a little better now. So 32 times 9, because 4 times 8 is 32 and 3 times 3 is 9. And then all of this over 7. And we get, okay, yeah, 288 over 7. Awesome. Okay, I'm going to cross my fingers that this is the right answer. Okay, 3, 2, 1. Oh, this one was 42. So maybe was there something that we did wrong here, perhaps? Oh,
I
okay. The question asks how many whole buckets of paint. So this means that Jack cannot get a fractional bucket number of buckets of paint. So we can only, I'm assuming Jack can only buy like entire buckets of paint at the store. So yes, we need 42 full buckets of paint because we see that 288 over 7 is like 280 over 7 plus 8 over 7. And 280, we can easily see that this is equal to 40 because 28 over 7 is 4, so 280 over 7 is 40. And then this is a little bit over, 8 over 7 is a little bit over 1, right? So 288 over 7 is going to be a little bit more than 41. So Jack's going to need 42 whole buckets of paint. Okay, awesome. Great job, everyone. So Cynthia, back to you. What do you think of the next problem?
Awesome. So our next problem, Caitlin buys apples, bananas, and cherries at the store. She can only buy whole fruits, and she buys a total of 13 pieces of fruit. Given that she buys at least one, but no more than 6 of each kind of fruit, how many different sets of apples, bananas, and cherries could Caitlin have bought? Assume that two fruits of the same type are identical. Okay, so Caitlin can only buy up to 6 of each type of fruit, which means if she were to buy 6 of each type, she would buy 3 times 6, 18 pieces. But she only buys a total of 13 pieces of fruit. So let's imagine she starts with 6 of each type of fruit, and then she's going to try and get rid of 5. And those 5 could be a mix of the 3 different types of fruits, right? So essentially, this problem has just turned into we have 5 things, 5 things, and we're trying to place them into 3 groups. And if you guys have heard of stars and bars, I think there's a lot of different names for it, sticks and stones, all of that. We can just think of placing dividers amongst our objects and trying to find places for those dividers, and that gives us the number of ways we can break those 5 things into 3 groups. So if we're trying to break things into 3 groups, then we need to place 2 dividers, right? Because imagine you place one here, so then you have a group on the far side, one in the middle, and then one on the other side. So now we have a total of 5 plus 2 objects when we include both the stars and the bars, or in this case, the fruit and the dividers. And we have 2 dividers. So what we get now is 5 plus 2, which is 7. Choose 2 because that's the number of dividers. And this equals 7 times 6 divided by 2, which is 42 divided by 2, which equals 21. And let's just verify that that's correct. And yeah, it looks like the answer is 21. So nice job to everyone who got that. This is kind of a tricky one. You do need to know stars and bars, but hopefully you guys remember that in the future if you didn't know it before. And yeah, Erica, do you want to help us through the next one?
Okay. Yes, sure. Okay. For any real number x, let brackets x represent the positive difference between x and the greatest integer less than or equal to x. For example, brackets 3.2 equals 0.2, brackets 4 equals 0, and brackets negative 1.2 equals 0.8. What is the sum of the values of k squared for the 5 smallest possible real numbers k that satisfy the equation brackets k equals 3/5? Special answer is a common fraction. Okay. Loaded question here. Well, the first thing I'm going to start off with is I'm just going to try to find these 5 smallest positive real numbers of k, right? And so our smallest positive real number k that satisfies the equation brackets k equals 3/5 should just be 3/5, right? Because really all these brackets mean is just that like the difference between like it's just like the decimal part of x for positive numbers. For negative numbers, it's like 1 minus the decimal part. But since we're not looking at the negative numbers here, I'm gonna look at just the positive numbers. And for just the positive numbers, brackets x should just be the decimal part of x. So that tells me that our 5 smallest k should just be 3/5, 8/5, 13/5, 18/5, and 23/5. Does anybody have any thoughts? Okay. Yes. So, okay, some of the values of brackets k squared. Okay. And now I'm gonna start by trying to find the brackets k squared, and I'm gonna see if there is a pattern, because if not, I feel like this could be a lot of work. Although this is math, so sometimes math is a lot of work. So first, k squared for 3/5 should be 9/25, right? And brackets 9/25 should just be 9/25. And so I'm gonna put our final like brackets k squared in what color should I do? Pink. I'm gonna make it pink. Okay, 9/25. And then this over here for 8/5, that squared is 64/25, right? And the decimal part of that should be 64/25 minus 50 over 20, 50/25, right? Because 50/25 is 2, and 64/25 should be between 2 and 3, because 2 is 50/25 and 3 is 75/25. So this should be 64 minus 50/25, which would give us 14/25. Which I think makes sense. Yes. Okay, and now this is starting to get into big number territory. 13/5, if we square that, we get 169/25, right? And the closest multiple of 25 to 169 should be 150. So the difference between this and the closest whole number should be 169 minus 150/25, right? Which should get us to 19/25. Okay, so I'm starting to see a pattern here. Um, just to verify, 18/5. Okay, 18 squared is, I believe, hmm, 324 over 25ths, which, okay, as it turns out, the decimal part of that, if we subtract 300 over 25th, should be 24 over 25ths. So it looks like our our final bracket k squared should be 29/25, right? Except 29/25 isn't less than 1. So our next bracket k squared should probably be, okay, if 29/25 isn't an option because brackets k would be like the decimal part of k, if given that it's positive, then maybe, okay, then I think this would cycle back around to being 4/25. Is this making sense to everybody? Did I go like a little bit fast? Okay, so I'm just gonna think about the reason why. Okay, the reason why this pattern is here. Um, well, everything. Okay, all of these numbers up here are in the form like 3/5 plus some integer, like some. Okay, I think I saw a suggestion from somebody before. I'm gonna call that integer a. Okay. Shout out to whoever it was that like put this into chat. But okay, all of these numbers can be expressed as 3/5 plus some random integer, random positive integer a. And when we look at this, okay, this squared should be like a squared plus 2 times 3/5 times a, and then plus 9/25, right? So we get, this is a squared plus 6/5 a plus 9/25. Am I looking at this right? And, well, we know that, oops, okay. And we know that the brackets means, for positive numbers, it means like taking that decimal part, right? And we know that a squared is definitely an integer. If a is an integer, then a squared has to be an integer. So we can just like ignore, if we want to find the brackets of this, brackets of k squared, bracket k squared is going to, we can just like completely ignore that a squared up here. And if we take a look at 6/5 over a, 6/5 over a is the same as 5/5 a plus 1/5 a, right? And then plus 9/25. And we know that 5/5 a is also an integer. So all this, because if we can ignore these integers here, right? So we get, all this is really just equal to 1/5 A plus 9/25. And not, 1/5 is 5/25, right? So if this is our like brackets k squared for every value of our k, then it makes sense that for every k that we're going up as a goes up, then it's going to increase by 5/25, right? Which is why we went from 9/25 to 14/25 to 19/25 to 24/25 and then 29/25, but that circles back around to 4/25 because we can chop off that 25 like 25/25, right? Okay. Okay, so that was a very long-winded explanation, but we need to find the answer to our problem, right? We need to find the sum of the values of these k squares. So I'm going to add these together. 9 plus 14 plus 19 plus 24 plus 4. Does anybody have an answer for me here? Okay, I'm seeing a 14/5. So 14/5 should be 70/25, right? And okay, so 9 plus 14 is 23 plus 19. Okay, wait. Maybe I'll just like write this out. Okay, go back up here. Okay, 9 plus 14 is 9, 14, 19, 24, 4, 23, 42. Okay, yeah. So okay, 66 and then 4. So okay, yes. 70/25, which is the same as 14/5. Okay. Okay, my screen is getting really messy, but okay. So this is our answer that we got, and I am going to hope that this is correct. And it was 14/5. So awesome job to everybody who got that in chat and like way faster than I did. So shout out to everybody who put 14/5 in chat. And for our next problem, I will hand it back to Cynthia.
Awesome. Yeah, that was a long one and a tough one, so nice job to everyone who followed that. Um, okay, now we have this inequality, and we're trying to find the least positive integer n that satisfies the inequality. So first of all, I used this earlier, but just in case people don't know what the long parentheses around those two numbers means. So if you have something like n choose k, then this is equal to n factorial over k factorial times n minus k factorial. So in this case, since we have n choose 2, then this should equal n factorial over 2 factorial times n minus 2 factorial. And if you don't know what a factorial is, it's just that number times all the integers, all the positive integers that are less than that number. So n factorial is n times n minus 1 times n minus 2, dot, 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 all the way to times 3 times 2 times 1. So if we look at the top and the bottom here, n minus 2 factorial will have almost all the same terms multiplied together that n factorial does, except for n minus 1 and n. So we can cancel a bunch of them out, and what we're left with on the top is n times n minus 1, and then on the bottom, 2 factorial is 2 times 1, but that's just equal to 2. So we have this. So let's just like put that into our right side here. So now we have n squared over 2 is less than or equal to, and then I'm going to write 1.01 as 101 over 100, just because I prefer working with fractions over decimals. And then I'll replace this and choose 2 with what we've got in here, n times n minus 1 divided by 2. And then this should equal 101 times n times n minus 1. Hopefully you guys can follow all the parentheses here. Divided by 200. I have a divided by 2 on this side, and I have 200 here, so I'm just going to multiply both sides by 2. And then I'm going to multiply both sides by 100 over n, just to try and simplify things if I have space. So right now what I have is n squared is less than or equal to 101 times n minus 1 divided by 100, and I'm going to multiply this by 100 over n, and I'm going to multiply this by 100 over n, and I can cancel out one of my n's here, right? And then I can cancel out both the n and the 100 on the other side. So this gives me 101 times n minus 1 on this side of our equation over here. So 100 times n is equal to 101 times n minus 1. So that gives us, I'm going to start writing up here because I have some space. 100n is less than or equal to, and I will expand our other side so we get 101n minus 101. Now just rearranging to isolate n, we get n is greater than or equal to 101. And since we're trying to find the least positive integer n that satisfies this inequality, and we know that n is greater than or equal to 101, then the least possible value of n is equal to 101. So that should be our answer. And let's check. Awesome. Yeah, n is equal to 101. Hopefully that made sense, and I'll toss it back to Erica for our next problem.
Hey, awesome. So for our next problem, we are doing number 18. Call a positive integer with at least 3 digits, boxed if it has a property that its first and last digits are the same and have values that are strictly greater than twice the value of any other digit in the integer. For example, 52125 is a boxed integer, but 63336 is not. How many 5-digit positive integers are boxed? Okay, so first of all, that is a lot to unpack. So this is saying, okay, what is a boxed integer? A boxed integer is if you have, let's say, okay, a 3-digit number, um, whatever number, like something here, and whatever's in these two. Okay, first of all, okay, these two numbers have to be the same, and whatever's in the middle has to be less. Okay, it has to be less than like half of that. So like for 52125, 5 and 5 are the same, and then 2 and 1 that are on the inside are both less than, okay, and 2 and 1, like twice the value of that is less than 5. Okay. So how many 5-digit positive integers are boxed? Okay, I'm gonna look at 5-digit, I'm gonna look at just 5-digit positive integers. And 1, 2, 3, 4, 5. So this is how this is a counting problem. And well, the first thing that this tells me is that, okay, I'm gonna just look at the digits that could be first and last. So like if our first and last digits are let's say 1, put this up here, 1, then the values on the inside have to all be 0, right? Because otherwise there's no way that like that's like the only possible way that we could have a box number with our outside numbers being 1. So there's one case of that, and same case with 2, because we can't have 1s on the inside because then 2 isn't greater than twice the value of 1. It's the same as twice the value. There's also only 1, which is just 20002. For 3, it gets a little bit more interesting because now we can have 1s and 0s in the middle. Sorry, I'm a little bit sick. But if it's 3 and a 3, then this could be 1 or 0. 1 or 0, 1 or 0, so 2 times 2 times 2. So there has to be, or there should be 8 boxed integers for any 5-digit number that starts with 3. And for 4, this should be, the numbers on the inside can still either be just 0 or 1 because 2's not small enough. So again, every number on the inside can be 0 or 1, 0 or 1, 0 or 1. So 2 times 2 times 2, which is again 8. Okay, so I'm seeing something interesting here, and that it's that all of these are coming in pairs. Okay, so the number of one of boxed integers that start with one and the number that start with two are the same. Same for three and four, and this makes sense, right? Because the values inside have to be if it's strictly greater, then it's like one and two they can both only have zero, and for three and four they can only have zero or one, and for five and six they're only going to be able to have zero, one, or two, and so on and so forth. And another thing that I'm seeing here is that this is a sequence of cubes, right? One is one cubed, eight is two cubed. And the reason for this is that technically I don't see any condition that says that like it has to be that the order of these three integers have to matter at all. So for every one of these no three numbers in the middle, they all have the same like options to be. Like in the case of one and two, well, not in one and two, in the case of three and four, all three numbers could be 0 or 1, 0 or 1, 0 or 1, so that'd be 2 cubed. And if we take this a little bit further, for the numbers, for any box number that starts with 5 or 6, the numbers on the inside should be able to be 0, 1, or 2, right? And so if there's three options for each of these numbers in the middle, so 3 times 3 times 3, and then this is going to be either 5 on the outside or 6 on the outside, and so we get both 5 and 6 are 27, which is 3 cubed. Is this pattern making sense to everybody? I hope so. And from a very similar line of thinking, I think 7 and 8 should both be 4 cubed, which is 64, 64. And then finally 9, our only number that can have 0, 1, 2, 3, or 4. So 5 cubed, which would be 125. Okay, so now we have all of these numbers, but we still need to add all of them together. So I see duplicates of 1, 8, 27, and 64. So I'm going to say, okay, this is 2 times 1 plus 8 plus 27 plus 64. And then we're going to add on that final 125 at the end, right? So this should be 9. Oh, okay, I'm going to pair these up. 8 plus 27 is 35. This is 64 plus 1 is 65. So 35 plus 65 happens to be 100, which is very nice. So we get 200 plus 125, and that should equal 325 total 5-digit boxed numbers. Does that check out? Okay, yes, I am seeing 325 in chat, so awesome. I'm going to check this real quick. And yes, okay, our answer is 325. So amazing. Okay, Cynthia, back to you for our next question.
Awesome. Okay, so our next question is a cube has the property that the sum of the numerical values of its volume and 12 times its edge length is numerically equal to 4 times its surface area. I'm going to write that down so that we can follow what this means. So let's let the side of the cube equal s. That means its volume can be represented as s cubed, right? Length times height times width. And then 12 times its edge length. So we're adding 12 times s. Oops, my pen is glitching a little bit. And that is equal to 4 times its surface area. Now the surface area of a cube is 6 times the area of each of its sides because a cube has 6 equal faces, I guess. 6, so 6 times, and then if each one has side length s, that means s squared. So that's the surface area, and then we have to multiply this by 4 again to get 4 times the surface area. So we can simplify that as 24s squared. Now we're trying to find, given that the volume of the cube is greater than 1, and the edge length can be expressed in the form a plus b root c for positive integers a, b, and c such that c is not divisible by the square of any prime numbers. And we're trying to find a plus b plus c. So we have s cubed plus 12s equals 24s squared. And I know that since s is the side length of a cube, that means that s can't equal 0, which means I can freely divide every term by s right here. So now I get this. S squared plus 12 equals 24s. And this looks like a quadratic to me, which is a lot easier than a third degree polynomial, and I can handle this um, with the quadratic formula, right? So now my quadratic is s squared minus 24s plus 12 equals 0. And if you recall, for ax squared plus bx plus c equals 0, to find the roots of that, we can do negative b plus or minus the square root of b squared minus 4ac all over 2a. If you guys know the song, you can just think of that. But let's just plug in all of our coefficients into this. So we know that our coefficient in front of here, since there's nothing here, we assume that this is 1. And we have negative 24, actually. Don't forget that negative sign. And then 12 is our constant term. So negative 24 gives us 24, plus or minus negative 24 squared is 576, I think. And then minus 4 times a times c. 4 times a is 4 times 1. And then times 12 is 48. So we're subtracting 48. And this is all over 2 times 1. Okay, now we get some nice calculations. 576 minus 48. You guys can put that into chat, but I believe it's 528. Is that right? Okay, I'm going to assume that it's 528. 24 plus or minus 528, which I can take out. I can take out 4 from that. 132, and then that's 12 times 11. Okay, so I can take out another 4. So that's 4 times the square root of 33 over 2, which is equal to 12 plus or minus 2 root 33. And then we're also given that the volume of the cube is greater than 1. So that means s cubed is greater than 1. And if s cubed is greater than 1, that means s is also actually strictly greater than, right? Okay, ignore this equal then. S cubed is strictly greater than 1, which means s is also strictly greater than 1. So one of these is going to be less than 1. Let's see. 12 minus 2 root 33. Well, root 33 is like a little bit less than 6. 2 times 6 is 12. So I'm guessing that 12 minus 2 root 33 is less than 1, which means the only one that works given the conditions of the problem is 12 plus 2 root 33. And then now what they're trying to ask us for is we're representing it as a plus b root c. And as you can see here, we already have it in that form, so that's pretty convenient. And we're trying to find what's a plus b plus c. So right here, a is equal to 12, b is equal to 2, and c is equal to 33. So we just add those up. 12 plus 33 plus 2 is equal to 45 plus 2, 47. And I think I saw a lot of people putting that in earlier. So great job to everyone who got 47. Yeah, I see people are asking when does the class end. Actually, since it's exactly 8:30 right now, I think we can start wrapping it up here. But thank you to everyone who came to solve some fun problems with us. I hope you guys had fun and I hope you guys learned some stuff. And hopefully you guys did well on the Math League problems this year.
Yeah. Like, it was really great to hear from everybody today. And I love how like active everybody was in chat. So it's been great solving these problems with you guys. Thank you so much for being here, everyone.
Bye, everyone.
Bye bye.